Okay. Helping me out in the chat is Fee, Emmanuel, and Keith, I believe. So if you guys have any questions, just drop them in the chat. I will try to be looking at the chat periodically. If I don't get to the question, then they'll like poke me and I'll address it. But yeah, let's go ahead and get started. So here's a neat little diagram to kind of illustrate the role of SLURM in HPC computing. HPC standing for high performance computing. So first on the left hand side, we have the login nodes. The login nodes are where you basically where you connect to the cluster and you're going to submit your jobs from there. The login nodes, as you can see, have access to the shared file storage system. So this is going to be your home drives and your scratch drives. And they can also communicate with the job scheduler. And then the job scheduler can communicate with the compute nodes. So on the right-hand side, you see compute nodes 1 through 6 and hundreds more because these are clusters. So they're basically groups of compute nodes. And the compute nodes also have access to the same shared file storage system that the login nodes have. So as you can see, the job scheduler SLURM in our case acts as the bridge between the login nodes and the compute nodes. So here's a quick recap of the file systems and user directories that are available on our clusters. So on Terra and Grace, you're going to have 2 file systems. These file systems are your home drives and your scratch drive. So everyone has a home drive, and that home has 10 gigs or 10,000 files. There's going to be 2 limits on each drive. So whatever limit you reach first is going to be the one that stops you. So if you have 11 gigs of data that you want to upload to your home, if you try to upload it, you're going to get an error that says disk quota exceeded. That just means exactly what it says it means, and that your disk quota has been exceeded for either the space or the file limit. So to see your current quotas, you can use the command show quota from the terminal. So log into Terra or log into Grace and then say show quota, and you're going to get a neat little printout that shows the directory that you have access to and its current limits, and it as well as its current usage. Your home directory is not, we're never going to expand your home directory. It's always going to be 10 gigs or 10,000 files. That's because we back up your home directories nightly. So any larger than 10 gigs or 10,000 files per user, and the backup starts to become absurdly large. So we won't work to increase your home directories, but if you need more space in your scratch, we could try to accommodate that. So your scratch by default has 1 terabyte or 250,000 files, whichever one you hit first. Your scratch is accessible at this path right here, scratch user and then $user. So $user is a variable for your username, which is going to be your net ID. In my case, scratch user Dylan points to my scratch. Also, anytime you log into the clusters, there's 2 environment variables that you have access to. The first one being $home, that points to your home, and $scratch, which points to your scratch. So $scratch is just a variable for this path right here on the left. Home is a variable for this path right here. Like I said, the 2 limits for your scratch are going to be 1 terabyte of space or 250,000 files. You can increase this to kind of fit whatever work you're doing. We recommend you submit quota increase requests through the Open On Demand dashboard. So that's going to be through our portal. If you go to our Open On Demand portal at portal.hprc.time.edu, and then go to dashboard, there's a button there where you could request an increase. If you don't want to do that, you could also just send us an email and request the increase. But we're gonna the reason we tell you to go through the dashboard is because there's some questions that we need to ask you about the increase, some justifications that you need to provide and stuff like that. So if you don't go through the portal and you just email us, we're probably just going to email you back and ask you to respond to answer all those questions. These increases for your scratch directory are temporary for 6 months. So after 6 months, we'll revisit your request and say, hey, okay, 6 months ago you requested this space. It looks like you finished your work, or have you finished your work? Can we reclaim this space? Because Grace and Terra are shared resources. So we have lots of users, and if everyone needs 50 gigabytes or 50 terabytes, then obviously there's not enough space for everybody. So we want to make sure that everybody has access and can use the resources. So yeah, these requests are temporary. If you are in a group, a research group, or something like that, and you want a group directory for sharing files, please send us an email. We could set up a group directory for you guys, and then your entire group will have access to that shared directory where you could store files, and everyone in the group has access to them. That's the better alternative. The anti-pattern that we don't want to do is make your Scratch drive open to everybody. So like you give everybody access to it. Please don't do that. That's not a good practice, and your data can just kind of go missing because people could accidentally remove it, and then you don't have a lot of recourse there. So yeah, if you're working in a group and you want a shared group directory, send us an email. We could work to accommodate that. Okay, so batch computing on HPRC clusters. If you were here this morning for the Grace primer, this is gonna look familiar to you, but we just wanna recap that real quick. If you're on campus, you connect to the network. From the campus network, so Timeout Wi-Fi, you SSH into the login nodes. From the login nodes, you create a job. We're gonna look at some job scripts in a second. Those job scripts are text files on the cluster, and you submit those job script files to SLURM using SBatch, and again, we're gonna look at that. And then the batch manager, SLURM in our case, takes your job script file, reads its parameters and the resources that you requested, and places that job into a queue. And then that queue waits for the resources that you requested to become available, and then they end up running on one of the compute nodes over here. So all these little lights that you see right here, these are all individual nodes, and that they run there. This is actually a picture of Ada, of our tired cluster, but that's the idea. Each individual light is a compute node, and SLURM finds a spot in the cluster for your job to run on a compute node, and then the output files are sent typically wherever you submitted the job from. So if you submitted the job from your Scratch, the output files will also be in your Scratch. If you're off campus, the process is exactly the same, but the one step that you need to do is you need to connect to the VPN. The clusters are behind the Timeout VPN, or they're part of the Timeout network, which requires the Timeout VPN if you're off campus. So you can still submit your jobs from Starbucks or Sweet Eugene's, as I like to do, but you need to connect to the VPN first. Okay, so here is what a sample job script looks like. And then I have SLURM up here just because this SBatch syntax, this is all SLURM syntax. So this is gonna be the same for Grace and Terra. So if you understand how to submit jobs on Grace, you're gonna understand how to submit jobs on Terra. It's literally the same system. So at the very top, we see the shebang, hashtag exclamation point bin bash. This is establishing that this is a bash shell. So we want to execute these commands in a bash shell. All these lines that begin with the hashtag SBatch capitalized, those are called directives, and they are the SBatch or SLURM parameters that SLURM is going to look at, and these parameters define what your job is. So it tells SLURM the resources that you want to request for your job. These top ones we call the necessary job specifications, and we'll talk about them a little bit more in depth later, but basically these first two set the job environment. Export equals none and get user env equals L. This replicates the user environment across the compute nodes that the job is sent to. The third line, job name, does exactly kind of what you expect to do. It sets the job name. So it tells SLURM, name this job, job example 1. Time sets the wall time. And in this case, the syntax here is hours, hours, minutes, minutes, seconds, seconds. This is telling SLURM, I want this job to have to be able to run for 1 hour and 30 minutes. Followed by end tasks. This sets the number of cores that you want your job to use. One thing I should mention, cores and processes are basically the same thing, or actually they're not basically the same thing, they are the same thing. So end tasks equals 1 says I want to use one, I want to start one process, one core, so I want to use one CPU. Beneath that you see mem equals 2G. This says I want to reserve 2 gigabytes of memory for this job, and this value right here is specified per node. So this says 2 gigabytes of memory per node, and then this output right here defines where to send the output. In this case, we're saying send the output or name the output stdout.%j. %j is a variable for the job ID. When you submit this job, SLURM gives it a job ID to keep track of it. So this %j will get replaced by like 1, 2, 3, 4, 5 or something like that. By saying just stdout.%j, this is saying wherever we submit this job from, the place you submit the job from is called the I think it's called the job submit directory. I think that's actually what the environment variable is named. But wherever you submit the job from, this output will get placed there. So you'll see a text file called name this, and that'll have all the SLURM output. And then if your program generates any output, that output will also get placed in the same directory as std out. Okay, so beneath the necessary specifications, we have the optional ones. These are optional. You can omit them. It won't affect your job, but sometimes people include them to help refine their job or to make their job a little bit more accessible. So the ones that we have listed here are the account. So this is going to refer to your allocation. So your project allocation, for instance, it's where your SUs are stored. So whenever you submit a job, AMS, which is the billing system, AMS reads this job file, calculates how many SUs, and don't worry, we're going to talk about SU calculation and what exactly SUs are later, but it determines how many SUs your job costs, and then subtracts that from your allocation. If you have login access to our clusters, you probably have an allocation. That's how you get access to the clusters. As a student, you get a basic allocation, and the basic allocations have 5,000 SUs. So to start with, you'll have 5,000 SUs, and this line right here is saying, SLURM, I want you to charge account 1, 2, 3, 4, 5, 6 for whatever this job costs. If you remove this line, because it is optional, you can remove it. SLURM will go to AMS, and AMS will say, okay, what's this user's default account? Charge the default account. So by default, SLURM charges the default account. If you want to charge an account that's not your default, you include this line, or you change the default account through my project. We'll demonstrate that in a second. These two right here, self-explanatory. These enable email notifications. Mail type all says, I want to be emailed when this job begins and when this job ends. And then SBatch mail user is your email address. So email me when it begins and ends, and then what email address you specified you want to send this to. Beneath your job specifications, you load the required modules. So you kind of replicate the environment that you're going to work in, and then you launch your program. So in this example right here, this person is running a Python program called myprogram.py. And in order to run that, he needs Python 3.7 along with the Intel 2018B toolchains. So in this example right here, after all these specifications, he's saying module load Python 3.7 and then run my Python program on the compute node. And this Python program has access to 1 core and 2 gigs of memory for 1 hour and 30 minutes, somewhere on a compute node that we don't know off the bat, but SLURM will determine. So let me just check this. Okay, so we had a question. How long can we keep the group directory? Good question. Group directories. Okay, the way group directories really work is that and correct me if I'm wrong, Keith, but I believe what the way we have them set up is that the files that are in the group directory are actually counted against the quota for whoever we set the group up for. So it's not like no, that's incorrect. Okay, so I think Keith can answer that. I believe the group directories can be. Oh, okay, the quota applies to the file's owner. So it goes by the file's owner. So if you ls minus l, whoever owns the file, that's where the quota is going to be. Like that's where the file is going to count against. As far as how long can you keep a group directory, it typically as long as you need it. Yeah, the group members can see your files. We don't have to worry about your files that affect their quota. And correct me if I'm wrong, Keith, but the group directories, the shared directories are indefinite, or as long as the group needs it. I don't think that they're not on the 6 month. Yeah, they're not on the 6 month is only for quota increases. So like if you specifically want 3 terabytes in your Scratch directory, that would be the 6 month limit, and then we revisit that after 6 months. Good question. Thank you. Okay, and we had a question. Using Numba Julia, should these modules also be loaded? Which is better or preferred, Numba Julia or what? Yeah, so if you're gonna, all the software that you are gonna use, you need to load. So if your job requires Julia or Numba or whatever, you're also gonna see like module load Python, module load Julia, module load, etc. You're gonna wanna load all of the modules to create your environment. It can get a little tricky when you load lots of different modules, you're going to want to make sure that those modules are compatible with each other in that they don't have conflicting versions. So maybe like one module uses a library that another module uses as well, but just a newer version. That could get kind of tricky. But ignoring the versioning issues, yes, every piece of software that you need to use for your program will have to be module loaded. So it's normal to see, you know, a few different module load commands. And then once you get a little bit more used to the module load system, you will just stack them on, you'll stack the modules on one line. So say module load Python, MATLAB, or Julia, or stuff like that. So you can actually stack them on one line, but it's probably easier when you're just starting off to kind of write them out explicitly. Good questions, guys, good questions. Next, okay. Important batch job parameters. I actually just went over these, so I'm not gonna stick too long. Yeah, I just explained all these. The time and tasks is the cores, the CPUs per job. Tasks per node is how many cores per node. And then memory is specified per node. That's kind of the takeaway here. When you're specifying memory on in SLURM, you're saying per node. And then you can also specify it by megabytes. However, I probably wouldn't ever specify with megabytes unless you want to be super refined. Typically specifying by gigabytes is a lot easier. It's easier to kind of wrap your head around that as well. Okay, mapping jobs to cores per node on Terra. So the reason I have a Terra example here is because Terra has far fewer cores per node, so it's kind of easier to demonstrate, but this principle applies to Grace as well. So on Terra, each node has 28 cores. So one little, this whole big box here kind of represents one node, and we've got 28 cores on this single compute node. So on this compute node, example A right here, this job says, I want to use 28 cores, and I want to put 28 cores on one node. 28 by 28 gives us 1. So we know 28 cores on one compute node. This is what that diagram would look like. Every core on that node is allocated to your job. That's good. Example B, 28 cores again, same amount of CPUs, but 2 compute nodes. N tasks 28, that didn't change. Tasks per node equals 14. So what we've done is we've split up half of the cores onto one node, half of the cores onto another node. So now these two nodes need to communicate with each other to finish the job. That's still good. Example number C, we do it one more time, split it again by 2, 28 cores, but we're splitting it up into 4 compute nodes. So we're saying 7 cores per node, and this is how that looks. 7 cores on 4 different nodes, same amount of CPUs, just split up across 4 different nodes. So the question is, why wouldn't you always just split your job up super small? And the reason you wouldn't do that is because the overhead of communicating between nodes eventually outweighs the benefit you get from splitting your job up. So eventually it'll just become so costly to have each node communicate with each other that it's not worth parallelizing. It won't be worth splitting it up anymore. So ideally you would have all the cores on a single compute node. This is the best case over here. However, you could probably tell that reserving an entire 28 core node to yourself is, you know, on paper, it's going to take longer for these resources to become available and your job to start running than it would for example C. So this is to demonstrate that you could fragment your job up, but at some point the overhead of communication is going to be too costly. So you're going to want to weigh that when you're submitting your jobs. You're going to want to say, is it better for me to just kind of wait out the resource time and wait for the resources to become available, or should I fragment my jobs and place them on nodes like that? Oh, okay, and on Grace, it's the same exact thing. It's just I should mention Terra is 28 cores per node. Grace is 48, so bit larger. There's basically 20 more cores per node. So it's the same math, just kind of do that division. 28 versus 48. Okay, job memory requests on Grace. So when you're specifying memory, remember the line in our job script that specifies memory is sbatch /mem. we're gonna kind of ignore. I want y'all to know that you can specify in megabytes, but gigabytes is probably the way we're gonna go. So to keep things simple, we're just gonna use a gigabyte example right here. So when you're saying sbatch double dash mem equals some number, you might be asking, well, how much memory do I have access to? So on Grace, the compute nodes have 384 gigabytes of memory. That includes the nodes with GPUs attached. So I was actually corrected from this morning. Each node, the GPU nodes have 2 GPUs except for the T4s. The T4 GPUs, there's actually 4 of them per node. Yeah, a little fun fact there. But regardless of what accelerator or what GPU is attached to the node, they all have 384 gigabytes of memory. So on those compute nodes with 384 gigabytes of actual memory, the usable memory, so the free memory that you're gonna have access to or that you can tell SLURM to request for your job is gonna be 360 gigabytes per node. And then if you wanna break that down to a per process memory limit, that's gonna that would be about 7,500 megabytes per core for a 48 core job. So there are larger memory nodes on Grace, and those larger memory nodes have 3 terabytes of memory. The usable memory for those 3 terabyte nodes is going to be around 2,900 gigabytes. So breaking those down, that would be about this value right here, 37,000 megabytes or 37 gigs roughly. So yeah, so just kind of remember what you're gonna want to take away from here is this value right here, the compute nodes on Grace, 384 gigabytes of memory, and the usable memory, 360. So on Grace, this value right here, mem equals, should not exceed 360 gigs. Okay, so let's talk about Terra. So same exact thing, sbatch double dash mem is our directive that we're playing with to adjust our memory value. On Terra, most compute nodes are going to have 64 gigabytes of memory, a lot smaller. So on the 64 gigabyte nodes, the usable memory is going to be around 56 gigabytes. So again, double dash mem equals xg. This x is not, you're not going to want to exceed 56 on Terra. 56 on Terra, 360 on Grace. Grace is the newer cluster, it's the flagship, it's really cool. So yeah, if you want to work over there, I totally understand. So the per process memory limit, so per CPU memory limit should not exceed roughly 2 gigs. No, thank you, Java. Nice. Should not exceed roughly 2 gigs for a 28 core job. The larger memory nodes on Terra are 128 gigs. Those are the ones with the GPUs, I believe. And so on the 128 gigabyte nodes, the usable memory is at most 112 gigs, which sets the per process memory limit. So per CPU memory limit to be about 4,000 megabytes, a little under 4 gigs for a 28 core job. Okay. How many, pop quiz, how many cores is this job requesting? So we see n tasks equals 80, tasks per node equals 20. How many cores is this job requesting? I'll give y'all a hint. There's no math you need to do for this one. So the answer is actually 80. So in this case, we're asking how many cores. So this is just straight up how many CPUs. I see what you did. D is the amount of nodes. So we said 80 cores divided by 20 cores per node gives us 4 nodes. But in this case, we're just saying how many CPUs, how many cores is this job requesting? In that case, it's just right here. N task equals 80. So 80 CPUs total on Terra. They will be split across 4 different nodes. So you're correct in that. And then this job will run for 48 hours. And then the output goes specifically to Scratch user Dylan output there. Okay, consumable computing resources. So we're gonna start talking about SUs right now. In your job file, you specify processor cores, how many CPUs you want to use, how much memory you want to use, and the wall time for your job. So the wall time, again, is how long your job can run for, and then whether or not you want a GPU or not. Those resources affect how many SUs or service units your job costs. Service units are associated to your billing account. You could see your billing account using My Project on the clusters. So let's see, if I log into Control L, I'm going to log into Grace. Okay, and now I'm going to say my project. So I see my billing account here. Clear my screen, do that again. So I see that I have this account right here with this account number. This is for this current fiscal year 22. It's my default account with an allocation of 5,000 SUs and none of them have been used. So it means I have a remaining balance of 5,000 and my PI's name is right there. So this is how you check your billing account. You can have multiple billing accounts. A situation where you'd have multiple billing accounts occurs when you as a user probably exceed your 5,000 balance and you want more SUs. So you go to your advisor and say, hey, I was doing your work. I used my SUs. Can you give me some? Your advisor goes and creates a startup account. So it's the same application that you did. You did a basic account application. Your advisor will go do a startup account application and they will be allocated 200,000 SUs here. And when they do the application, they can list you, the student, as a researcher under their account, and they can sub-allocate from their 200,000 SUs into your account. So when they do that, your output will look like this one right here, where you have two lines. One is a 10,000 SU allocation, and the other is a 5,000. So this 10,000, this could be whatever. This could be 20,000. This could be 100,000. It could be this. This value is going to depend on what your PI, what your advisor professor decides to give you. So you'll get a whole nother billing account that's accessible to you and that you could charge SUs to. It's still the same login, so you're still gonna SSH and connect with your NetID. The separation is at the billing account level. So remember, you're always gonna log in with your NetID and password, and then you're gonna run my project to see the allocations that you have access to. So yeah, so DPUs are included here because with the current billing setup right now, if you request a GPU in your job script, you're going to be billed for all of the cores on the node. So let's use a Terra for an example. So on Terra, the GPUs, there's 2 GPUs per node. So if you request one GPU, if you request one GPU and 1 core for 1 hour, and 2 gigs of memory, you're still going to be charged 28 SUs because you're being charged for the entire node. You're being charged for all of the CPUs on the node if you request 1 GPU. So the moral of the story is if you request a GPU, you might as well request all the CPUs because you're going to get charged for them anyway. It currently works like that on Grace right now. We're trying to implement it on Grace so that we're trying to change it so that you only get charged for the CPUs that you get billed that you request in your job script. Right now, that's a high priority thing for us. But just so y'all know, when you request a GPU, you get charged for the entire node. So that's why GPU is right here in this area. Other resources: software licenses, software licenses or tokens. Some software is restricted behind licenses, and some of that license restricted software is hosted on our clusters, and we also host the license server. So the example that we use is ANSYS. ANSYS is a licensed software, and so when you run it, you need a license. Since we host a license server, whenever you module load ANSYS, and then you run ANSYS on the cluster, the license server automatically checks out a ANSYS license for you and whatever you're doing with it. If there are no ANSYS licenses available at the time that you try to run your job, you're going to get an error and the license server is going to say no licenses available. I actually don't know what the error says. It's pretty clear though. Like when you see it, you'll know that there weren't any licenses. I just don't know what it says verbatim. But licenses are first come, first serve. I don't really think that we've had an issue with them running out lately. However, like that doesn't mean that doesn't happen. Especially around the time that deadlines start coming around. Later on in the semester, we could see like spikes in usage and there might be no licenses for a while. So just so you're aware of that, some of the software is behind licenses. We have a license status checker tool. You can access it by saying license_status. License_status -S will search and return all the licenses for a specific software. This example returns the licenses for ANSYS. I think if you just say license status minus A, that shows you all of them. But for the complete list of options with the license status checker tool, you could say license status underscore status minus H, and that's going to show you all the options that you have. First come, first serve is the takeaway from there. Okay, I promised we'd talk about SUs, so let's talk about SUs. An SU on Terra is equivalent to 1 core or 2 gigs of memory for 1 hour. That is the same for Grace as well. So we have this little table here, number of cores, gigabytes of memory per core, and total memory, hours, SUs. So row 1, 1 core, 2 gigs of memory for 1 hour is 1 SU. 1 core, 3 gigs of memory for 1 hour, you get charged 2 SUs. So we kind of round up here. 1 core, 56 gigs of memory for 1 hour is 28 SUs. So in this example, we're saying we only want 1 core, but we're asking for all the memory on the node. So because you're asking for all the memory on the node, the train of thought is if you have all the memory on the node, nobody else can really run on that node because a core can't do work without memory, or it could barely do any work without memory. So because you've requested all the memory on the node, you're going to get charged for all of the you're charged SUs equivalent to having the entire node for 1 hour. Same deal with cores. If you ask for all the cores but only a little bit of memory, well, there's a whole bunch of memory on the node, but there's no cores for anyone else to use. So you're still occupying the entire node. So that's why you get charged 28 SUs. The exact definition of a service unit, like the exact mathematical definition, is available on our wiki at this link right here, HPRC AMS. AMS, again, is the account management system. So when you're dealing with SUs or billing accounts, AMS is kind of the acronym that you're going to be looking for. And then service unit there, you could go see the mathematical definition and play around with it if you so choose. Okay, batch queues. Job submissions are auto-assigned to batch queues based on the resources requested. So the resources requested being the number of cores and the wall time. So the queues are organized basically by how long your job's going to run for. For example, on Grace, the short queue has a limit of like 1.5 hours. So if your job runs for longer than 1.5 hours, it's going to get placed in a bigger queue for bigger jobs. Some jobs can be directly submitted to a queue. The example for that are GPU jobs. So if you're going to use the GPU, you can add that line, partition equals GPU, that says, I want this job to run on a partition that has a GPU. You're also going to see some job cubes in a second that specify how to request GPUs. GPUs in SLURM speak, in the job scheduler world, they exist as resources, special resources on the attached to the nodes. So there's a line where you request a specific resource, and I have some syntax for that in a second. Jobs that have special resource requirements are scheduled in the special queue. So special resource requirements. This morning we had an example. Someone asked a great question. They said, so the limit for GPU queues is 4 days. What if I have a GPU job that might run longer than 4 days? Let's say this GPU job might run for 5 days. The answer to that is the special queue. That's the reason we have the special queue. It's for these corner cases that don't fit into they don't fit great into a category. If you email us, we could set up a time where we could allocate those resources to you manually, and you can run your job. So if you go to our wiki, hprc.timeout.edu/wiki/Terra or Grace, and then batch queues, you could read about the specific batch queues for whichever cluster you're looking at. And if you have any questions about scheduling a special job, send us an email. We could work out a time to manually allocate those resources to you. Synfo. So Synfo shows you current queues. Synfo is the command you run on Terra or Grace. This example right here shows the output from Terra. So let's go to Grace. I'm going to Control L to clear my screen. And I'm going to say SINFO, Synfo, Synfo. So right here, we see the first column is partition. This is going to be your queue. So, oh, sorry, it has a 2-hour time limit. Why was I thinking 1.5 hours? Oh, because the job script was 1.5 hours. That's why. Yeah, 2-hour time limit. Sorry. Yeah, 1.5 hours is kind of an awkward amount of time. Anyway, this first column right here is the queue. SLURM calls them partitions. They're queues. Just kind of think partition and queue synonymous. So we see the short queue has a limit of 2 hours. So if your job is less than 2 hours, it's gonna get put here. It's less than 2 hours, and it's gonna use less than 32 cores. This job size right here, and then the next two columns describe how many nodes and CPUs are available. So AIOT stands for available, idle, offline, and total. As you can see, the entire short queue is pretty much all the nodes in the short queue are being used, but there's about 1,653 idle CPUs in the short queue, or that are accessible by the short queue, I should say. So yeah, Synfo shows the current queue status for the cluster that you're on. So you could see short, medium, long, extra long, BNC for those portal jobs, GPU for all the variety of GPUs we have, and then those big mem 3 terabyte nodes are right here too. And then here's the special queue that I was talking about. So if you have a job that's not going to fit onto one of these like pre-described queues, you email us and we'll find a spot for you in the special queue. Okay, how do you actually submit your job? So to actually submit your job, you're going to say SBatch and then the name of the job file. So ideally, you're going to write the job file on the login node, or you're going to write it on your computer and then transfer it up to the login node. Once it's on the login node, you say SBatch and then the name of the job file, and SLURM takes it from there. So this example right here says, okay, we've submitted example 01, and we SLURM named it job. It assigned a job ID to it, job 161997. And then it tells you the AMS accounting stuff beneath it. It says your job was charged as below. From this project account, this allocation number, we've with this balance, 1,687 SUs, we've charged you 3 SUs. So now this job has been submitted, and it's going to be first pending. When your job is pending, that is SLURM saying, okay, I got your job, I read the resources, now I'm waiting to find out where your job can fit in on the cluster. Again, same idea on Terra and Grace. It's gonna behave the same exact way. The resources that you request in the job script are going to be read by SLURM, and then SLURM's going to wait to see where those resources become available, and it can lock them down for you. Obviously, requesting a lot of resources, so a bigger job is going to probably be pending for longer than a small job. It just kind of depends on how busy the cluster is at any one given time. Small jobs that are like less than an hour typically run like instantly or near instantly, unless it's like finals or some big deadlines coming up. But if you're requesting a lot of resources for your jobs, you could see like an hour or so wait time, especially if you're requesting like GPUs and high popularity stuff like that. So okay, you submitted your job. How do you check the status of it? SQ minus U and your net ID. That's how. So if you say SQ minus U and then Dylan, you can see all of the jobs that I have submitted that SLURM is currently handling. So those are going to be jobs that are either pending or they're running. Once the job is finished, it's not going to be an SQ anymore. So again, SQ only shows you jobs that SLURM is currently handling. So either jobs that are pending or jobs that are running. This is the output of SQ, and you can see the job ID, the name of the job, the user, what partition, aka which queue it was sent to, how many nodes the job is using, how many CPUs it's using, or how many nodes were requested, sorry, and how many CPUs were requested, the current state of the job, how long the job's been running for, how much the job has left, the start time, if there is one. And if your job is pending, SQ will give you the reason. So resources means that SLURM understands your job and is waiting for the resources that your job needs to become available. If it says none, it's probably because your job is running. And then when your job is running, you get a node list, and the node list has the host names for the compute nodes that your job is actually running on. So this bottom job right here, we can see is running on 4 nodes, and we have a node list right here. So it's running on TNXT 0401 to 0404. So if you wanted to actually go onto the compute node where your job is running, you could SSH onto TNXT 0401 and your job would be running there. That's kind of more for like troubleshooting and stuff. You really wouldn't need to move to the compute node for any reason, but SLURM does tell you where your job is running. Okay, here's an example of a SLURM job file. This is a multi-core single node job. So in this case, we're saying / nodes equals 1 and tasks per node equals 14. So notice up here in this necessary job specifications area, we have this new directive called --nodes. I did not mention this before. So there are a lot of SLURM directives. There's a whole lot of them. The ones that we kind of include in the necessary job specifications are the ones that are probably the easiest to understand, and they're just what you need to get your jobs up and running. They're a solid like quick start guide. They're by no means an entire exhaustive list of all the directives there are, because there's quite a few. It'd be really, really hard to kind of talk about each one specifically. Definitely out of the scope of an hour-long primer. But just kind of understand that there are a lot of other SBatch directives that you can give SLURM. If you are so interested that you want to learn more, you could just Google the SLURM directives, and you could find the SLURM documentation and read about them. This example right here, I wanted to just kind of let you know that there are other directives outside of what we kind of deem the necessary ones. And in this case right here, we're explicitly saying, I want to use one node. You could implicitly say that by assigning, like we did on that A, B, and C slide, where we said, okay, 28 cores and then 14 cores per node. In that case, you're implicitly saying, okay, I'm going to need to use 2 nodes because you're dividing 28 by 14. In this case, we're explicitly saying, okay, 1 node, 14 cores per node. That is fine too. That's not going to throw any errors. And then beneath that, we're saying mem equals 28 gigs. Remember, memory is specified per node. So each of these, if you want to define memory per core, so how much each process has access to, you divide 28 gigs by 14 cores, which gives you your memory per core. That's kind of the takeaway I wanted to show you guys here. Okay, SLURM job file, multi-core, multi-node. So we're using many cores on many nodes. This is kind of a funny example because we're saying 8 tasks and then 2 tasks per node. So very similar to how we had the 28 cores divided by 4. So we had 7. Same deal here, 8 cores total, but only 2 per node. This is, like I said, this is a very funny example. You really wouldn't ever do this in practice, but I wanted to demonstrate that you can take a large number of cores, or you can take any number of n tasks, aka cores, and divide them up as you see fit across multiple nodes. Again, it's really not going to make a whole lot of sense to kind of do that. It's going to take some trial and error to kind of figure out what the sweet spot for you is in terms of how long your job takes to run and the efficiency of your job. So is your job actually using the resources that it is requesting? So one thing to note here is that these resource requests in your job file are just that, they're requests. So you're telling SLURM, hey, I want my job to have access to 2 cores per node and 2.5 gigs of memory per node. So when you tell SLURM is going to give your job that much memory and that many cores to work with, but it's up to your job, the code that you write and the program that you run to actually use those resources. It is possible to request 28 gigs on a node and then only use 1 gigabyte. In that case, you're being charged for all 28, but you're only using 1 gig, so it doesn't really make any sense. And we will show some ways to kind of list the node utilization, hint, later on. So, and this one charges you 288 SUs because the time is 1 day, 12 hours. So this is a very, very long, that's why I said this is a funny job. 1 day, 12 hours for 8 cores across, for 2 cores across 4 nodes, so 8 cores total. Okay, SLURM job file, serial GPU. So I promised I'd show you how to request a GPU. So the syntax for that is this bottom green box here, ~gres equals GPU1. So that's saying is I want you to reserve 1 GPU for me, and then put me in the GPU queue. And in this case, I wanted to highlight n task equals 1. So we're asking for 1 core, 2 gigs for 1 hour. So you might think, oh, this is going to charge me like 2 SUs or maybe 1 SU. But in this case, we're actually being charged 28 SUs. Again, because when you reserve at least 1 GPU on a node, you get charged for the entire node. So we're basically reserving this entire node and we're being charged, or we're only reserving 1 core on this node and 1 GPU, but we're being charged for the entire node for an hour. That's the takeaway here. And this is how you actually do it. Gres equals GPU :1 and partition equals GPU. So then you might be asking, okay, well, Dylan, Grace has multiple kinds of GPUs. How do I specify which kind of GPU I want to use? And to that, I say, well, here you go. Thanks for asking a question. SLURM job file serial specific GPU. So in this case right here, it's the same Gres syntax that we're saying, but this time we're saying Gres equals GPU :RTX :1. So this is going to request the GPU with the RTX tag, which is the RTX 6000, I believe, on Grace. So you'd use this on Grace. If you tried to Gres this RTX GPU on Terra, you'd probably hopefully get a SLURM error that says, hey, I don't know what RTX is. Because I believe they are, if I'm not mistaken, they're K80 NVIDIA GPUs. They're not RTX GPUs. But to specifically request a specific kind of GPU, still Gres is the resource reservation syntax in SBatch, and you say I want to reserve a GPU, specifically an RTX GPU, and specifically one of them. And then same thing, double dash partition equals GPU. That puts you on the GPU partition. And then the optional job specifications beneath that and the first executable line. Okay, other types of jobs. MPI and OpenMP jobs. MPI and OpenMP jobs are they're going to be your parallel jobs. They're going to be jobs that run across multiple nodes. That's when you need to use a message passing interface to more efficiently communicate between nodes. As you start running larger and larger jobs and you want to run them in parallel to really capitalize and benefit from the use of large amounts of cores, as in more than one node's worth of cores, you're going to start using MPI and OpenMP. Your job, the code that you run, so like your actual, the program that you write will have to be written in such a way that it could benefit from parallelization using MPI or OpenMP. Visualization, these are the GUI jobs. So that's going to be visualization jobs can be run on both Ada and Terra. That should say Grace and Terra. More details on that. That is the portal. So if you go to the portal, I think Fee put that link there at the very start. Portal.hprc.time.edu. You could launch interactive jobs. Those jobs get sent to they run in the VNC queue. If you remember in Synfo, right here, yeah, Synfo. There's this VNC queue somewhere right here. These are actually for the portal. So whenever you go there and let's say you want to run like ANSYS or Abacus or something from the portal, from your web browser, it creates a virtual terminal on a GPU node on Grace or Terra, and it launches the GUI of the application, and then it gives you access to whatever resources you request. So in the on the portal, there's a little job builder where it asks you how many cores do you want to use, how much memory do you want to use, how long do you want this job to run for. And it runs all that. So those are visualization jobs, and that's through the portal. Those run on GPU nodes. I think you could actually tell it. There's a toggle there and says, okay, actually, I don't want this to run on GPU. So for some reason, you want to run a visualization job not on a GPU. For a large number of concurrent single core jobs, so tons of concurrent small jobs, you could check out Timeout Launcher. There's a wiki page on it right there. If you go to our wiki, hprc.time.edu/wiki, and you search Timeout Launcher, it'll be under software. It's useful for running many single core commands concurrently across multiple nodes within a job. It can be used with serial or multi-threaded programs, and it distributes a set of commands from an input file to run on the cores assigned to a job. So you give it an input file and it sends that command to the cores assigned to a job. Can only be used in batch jobs, so you can't run this from you can't run this interactively. You're going to have to write a job script which calls Timeout Launcher in it. And if the Timeout Launcher job gets killed, you can resubmit the same job to complete the unfinished commands in the input file. So pretty neat. This is a wrapper that was written by one of the staff members here. So yeah, if that sounds like something that that your research or your jobs can benefit from, definitely check that out. Okay, job submission and tracking. So I said to submit a job, you say SBatch. SBatch the job file, submits it. SQ is going to list the jobs that are currently running. Remember, you're going to want to use SQ -u and then your username to see your jobs. If you say SQ without the -u, it's just going to show you everybody's job on the cluster. That is not really useful at all. So SQ minus U and your username. You could say S cancel to kill a job. When you S cancel the job, you're going to want to give the S cancel command the job ID. You get the job ID from SQ. S account SACT. This is for showing information on jobs. It's there, but I think the more important items are LNU, PE-stat, and CEF. So LNU stands for list node utilization. That was my hint earlier, and it shows you resource usage for a job. PE-stat shows the resource usage for a running job, and then CEF is so you could check the CPU or memory efficiency for a job. LNU and CEF need the job ID. PE-stat you use with the username. So these are the three that I would remember: LNU, PE-stat, and CEF. Therefore, tracking the efficiency of your job, aka the resource usage. So if you requested 28 cores, you could see, okay, I had 28 cores. Now, what did my job actually use? Did I use 28 cores? What was the efficiency there? Was I efficient with my cores? Was I not efficient? That sort of thing. And as far as remembering which ones use job IDs and which ones use usernames, not super important. If you try to use LNU with the user, it'll just tell you, hey, I want a job ID. And then you can go find the job ID from SQ. And same thing with PE-stat. If you give PE-stat a job ID, it's gonna say, oh, no, I don't want a job ID, I want a username. Okay, so how do you check your SU balance? I mentioned this already. To check your SU balance, you just say my project. It's gonna give you a list of all of your project accounts. In this case, we see 3 project accounts. So this guy has access to 3 allocations. To specify a project ID, okay, yeah. So this is the optional specification right here. So in SLURM, if you want to charge a specific account, you'd say SBatch minus A. We went over this. This is a optional specification. If you omit this, it's going to charge your default account. So the default account for this person is this one right here. This middle item, 5,000 balance. It had a 5,000 allocation. They've used 71 and they have a balance of 4,928. That's their default account. So if they omit this minus A account number directive in their job file, that's the account that's going to be charged. You can change that default account. So this person wanted to change the default account to his professor's account, to John Doe's sub allocation. He could say my project minus D. So you're calling the my project command again, but you're saying minus D to change the default, and then you set the account number to whatever account you want to be default. You can only set the accounts to default if you have permission to charge to them, and you only have permission to charge to the accounts that you see here. So if you don't see the account in the output of your my project command, you're not going to be able to set it as your default, and you're not going to be able to set it. You're not going to be able to charge SUs to it. If you tried to put my account number, or if you tried to put one of these account numbers in there, when you submit the job, SLURM will tell you you'll get a SLURM error that says like, I don't remember what that error says either, but it'll tell you invalid account to charge, invalid billing account. I think it's something like that. If you need help using the my project command, my project minus H will show you the options for the my project command. Okay, similarly, if you try to SBatch submit a job and you don't have enough SUs to cover the job, you'll get this error. SBatch error, your account's balance is not sufficient to submit your job. In this case, this person needs to either adjust their default account to charge an account that has a balance, or inside the job script for the file, add a line, add this line, the optional line that specifies an account that he has access to charge and that has a balance to cover the job. This is an expensive job. This job requests 18,218 SUs. So it's a pretty big job, and he's only got 382. So he's going to be messaging his professor pretty soon. Again, as a student, you need your PI to transfer you more SUs. If you are a PI, so you are a faculty member, then you will apply for a startup account. The startup accounts, you could access the application for them on our website, exactly where everyone else applies, hprc.timeout.edu/apply, and then you'll put in your net ID, you go as staff or faculty, and then find new startup. So startups are eligible for, or faculty members are eligible for 2 startups per fiscal year. Each startup is allocated 200,000 SUs. So your first startup will have 200,000. If you exceed those, you can apply for another startup. for another 200,000, and you'll have a total of 400,000 SUs from your startups for that fiscal year. If you exceed that balance, you can go back and apply for a research account, which start at 2 million SUs. They just take longer to get approved, and they're scrutinized much harder than the startup accounts. So in short, when you're running out of SUs, if you're a faculty member, apply for a startup account. If you're a student and you run out of SUs, you need to ask your PI or your professor or your advisor to apply for a startup account, and they can sub-allocate SUs to you. Okay. List node utilization, LNU. So here is some output examples from an example of output from LNU. So when you run LNU, remember you give it a job ID. You'll see the job ID, the name of the job. You'll see this bottom stuff right here. You'll see the host names that the job ran on. So remember I said that your jobs, like when you SQ, you get a node list. So this is that node list broken down. So it says TNXT0703. This is the actual name of the compute node that it ran on. That compute node had a CPU load of 26.99%, pretty low CPU utilization here. It shows the free mem, how much free memory there was, how much memory is available, and then in a similar sense to the Synfo output, we see the CPU like available, idle, offline, total. So in this case, it had pretty low utilization here. So note CPU load is not the same as percent utilization. So that's not the same as like your core was running super efficiently. LNU is a great place to start, but PE stat is a little bit better. When you use PE stat, you use it on a user, remember? So PE stat on a user, LNU on a job ID, PE stat minus U, and then Dylan, for example, for me, or whatever your net ID is for you, will show you it will show the node utilization across all nodes for a running job. So the job has to be running when you do PE stat on it. And in a similar way, we see the host name, the partition, the node state. So it was allocated. And then right here, this is the number you're gonna want to be looking at, CPU load. So low CPU load utilization will be highlighted in red. So this is saying, hey, you requested a lot of CPUs, of the CPUs that you requested, you're not really using all of them. You're using like 16% of them. So maybe you should consider reducing the amount of CPUs that you're requesting. In that case, you're going to save some SUs, and you're going to see your job potentially start running faster, like begin running. It's going to be pending for longer. A good CPU load utilization will be highlighted in purple. And then ideal CPU load utilization is displayed in white. Red, bad, purple, okay, white, good, with PE stat. Okay, and then some job environment variables. These are just useful to remember. SLURM job ID refers to the job ID of the job. So if you are writing a job script and you need, you're gonna want to refer to items that the job creates. This is where these job environment variables will come in handy. So again, SLURM job ID refers to the ID of the job that it will create. The SLURM submit directory is the directory where the job was submitted from. So if I submit my job from /scratch/user/Dylan/job1, that directory job1 is going to be the SLURM submit directory. $scratch is the same as it's always going to be. It's going to be /scratch/user/your net ID. That's going to be for each user. And then you have also temp dir, which is the temporary work directory that SLURM has access to on each node. And I believe that is local to each node too. So if you need to store some files real quickly for your job, you don't want to take up your space for your quota, you can utilize temp dir. We also have Timeout Batch, which is a automatic batch job script that submits jobs for the users without the need of writing an entire batch script. You can access it by saying Timeout Batch. But before you do that, I would suggest running Timeout Batch --help and kind of running through the help guide there, so you kind of understand how to use it. It basically goes in the place of writing an entire job script. So if you don't want to sit down and create an entire job script, you can use Timeout Batch. However, I will, as like a little pro tip, these job files that I kind of showed you here, these are available on our wiki, hprc.timeout.edu/wiki. If you go to either Grace or Terra, you could find the batch job examples, and you'll see these this text or very, very similar text, a lot of what users, first-time users or new users do is they take this text here from the wiki, copy this, paste it into a text file, upload it to Terra or Grace, and then they just modify the parameters that they need to tweak. So if they want the job to run longer, they just adjust the time. If they want more memory, they just adjust mem. It saves the time of writing an entire job script, and also you get these nice little comments here that kind of remind you what the jobs like what each parameter does. So I highly recommend that. There's examples from nearly every kind of job you could think of. I just kind of included a few very common ones here just because we only have an hour and don't want to overload you guys too much. But our wiki, hprc.timeout.edu/wiki, has links to all of our quick start guides for Grace and Terra, and there's extensive documentation on the jobs, and in much more detail than we could cover in a quick hour. The portal's there. You can access Grace and Terra. Curry's not there anymore. The command line, you can launch jobs, you can compose job scripts, and you can launch interactive GUI applications. Again, that portal is portal.hprc.timeout.edu. Okay, and then lastly, I want to plug our continued learning. So we do have a YouTube channel. It's called Texas A&M HPRC. If you are interested, I'd say please go subscribe. I like watching that YouTube channel grow. It has videos on tutorials on doing things like logging into the cluster, transferring files to the cluster, submitting jobs. I believe there's some for making applications, and we're always adding little small snippet tutorials on there. The students in the help desk, we work on that a lot. So if you guys find that useful, those videos are there. Then also our wiki page, which I've already plugged, hprc.timeout.edu/wiki, has the wealth of our knowledge. I highly recommend going there and familiarizing yourself with the contents. If you ever have a question, that's probably the place that I would start. And then if you can't find your answer there, then yeah, go ahead and send us an email. 9 times out of 10 though, whenever I forget something, I just go straight to the wiki and start reading it, because it has a very good amount of knowledge that we've kind of compiled there. So yeah, that's all I've got for you guys. So if anybody has any questions, I'll be happy to answer them. Otherwise, I really appreciate you guys coming, and I hope you guys have a great Friday. So feel free to drop your questions in the chat. And feel free to drop off if you guys don't have any more questions. Like I said, I appreciate you guys coming, and I hope you guys have a great Friday. I will stick around for just a moment and see if any questions pop up. Okay, with the absence of questions, I think we can, I'm gonna